All right, and we are live. You want the link?
I mean, I can pull it up.
Live. You want the link?
Okay, go ahead.
Apparently, you can get audio through HDMI. I guess I knew that, but I haven't actually seen it work before.
Yeah, my monitor always happens on the color screen out, like why I'm not able to get audio from my speakers.
I remember whenever I tried to call in for those workshops.
Yeah.
Is it working? No. Yes. Nope. Yes. Okay. Should we start?
I think so. Yeah.
Okay. So before we move on to more complex, well, not more complex, just sort of tuning networks and looking at a bigger case study, I wanted to quickly talk about a couple of applications that could potentially use, recurrent networks or not. So I know. Well, yeah. Let's think about this one, right? So the anomaly detection and specifically things like credit card fraud. Obviously, credit card companies today have to evaluate sort of your transactions on the fly as you're making purchases, and sometimes they'll say, nope, this one looks like it's fraudulent. We're going to deny it and make you call us and tell us that yes, you really do want to buy 13 tons of refrigerators before we approve the purchase. So the question is, might some of this neural network stuff be useful? And if so, how and what kind of things might be difficult? And what particular methods might you try to apply? So I guess maybe I shouldn't have put as much text on the slide and made you guys think about it. But let's start with just the basic stuff, right? So the type of problem is a classification problem, I would say. Each transaction coming in, I want to say, yes, it's fine, no, it's not fine, or maybe there's a problem. So there's various thresholds. The input could potentially be huge, right? I put in a few things, right? One obvious thing is what your recent purchases are. If I know that over the last, 3 hours you've made purchases at, a Starbucks in Chicago and a CVS in Chicago. If I see 15 minutes later a transaction in Poland, maybe that's suspicious. Probably you also want to have bigger history, right? So I know what kind of thing to tend to buy. And you probably also want to have some kind of, you can think of it as collaborative filtering, right? Statistics on your overall population, right? So even though you've never made this purchase, other people who seem to be like you have. So yeah, do you think neural networks would actually make sense for this kind of problem? If you were in charge of fraud at, I don't know, Visa or elsewhere, would you actually say, you know what, I'm going to use neural network or try? Or would you do something else?
To me, it's more like this is an outlier detection for anomaly.
Yeah. So it's definitely an anomaly for outlier detection problem. You still need to figure out what technique you want to apply to solve it. So you could try to make a network that made a prediction and use that for outlier detection. In some ways, right, I think the reason I might try something like neural networks is that it's another place where it's hard to describe explicitly what the rules should be. I suspect that certainly I'm sure when people started doing this 30 years ago, they probably did, right? They said like, oh, if the transaction is over such and such amount, and if it's in a different country than you had a transaction a few minutes ago, it's fraud. But I suspect that at this point, there's probably a big and complicated enough set of rules that it would be tempting to say, you know what, I'm just going to learn from the past history. And we have tons and tons of credit card data if you're Visa. So you might be able to do it. Why might you not want to do it using neural networks? I know it's a hard question.
I think you probably need a very large recurrent network structure.
Right.
So you want to see the whole sequence.
Right. So one problem is if I think it's important to have a lot of history, right? So it's not just like, oh, your last 5 transactions that matter, but it's your last 500. If you just do naively try, you know what, I'm going to feed this whole sequence of data into a recurrent network, it's not going to work because we just talked about why you can make it stretch to maybe 80 or 100 or something inputs to your sequence with all the tricks for LSTM, et cetera. But much beyond that, I think no one's been able to do using just a single network. So you'd have to have some way to encode the past that's sort of more structured. And I think the other problem is it is anomaly detection, right? And so even with lots of training data, the vast majority of the time, it's going to need to spit out, yeah, it's fine. And so it tends to be hard to make good classifiers for very rare events. I guess that's true for many other techniques as well, but I'm really curious, actually, if someday I'll find someone who does fraud at the big card companies, whether they're actually trying neural networks or not, right? Or whether they're actually still have a bunch of people hand tuning a giant database of rules or something else. But yeah, so there's things like, okay, how do I actually feed in that statistics about other users? And you can imagine a hybrid model where you might have an RNN looking at your last 10 or 20 transactions, spitting out some estimate that you then feed into some other type of model, decision tree or something, as just one input.
An interesting application could be simulating potential fraudulent transaction data.
Yeah.
You're trained with
See if you can generate fraud.
Yeah.
Or
simulating potential fraudulent data. Given a certain set of sequences,
kind of like Nietzsche. Yeah, trying to make a model and use it to predict stuff. Interesting, because then if you can get your hands on that model, then you can figure out what kind of things won't get caught, and you can make lots of money until you get arrested. So one reason I also wanted to talk about this particular example, which comes up a lot with neural networks, is this explainability point, right? That you need to explain your decision sometimes, maybe. Certainly in some applications, maybe in this one, right? If someone says, why did I get rejected? That's ridiculous. If you have a giant database of rules, you can go back and say, okay, you know what, here's why, right? We had a rule that said, if your name is Victor and you have a purchase of more than $500, we reject it. But if your explanation is like, well, this giant pile of 1 million parameters or 1 billion parameters said that the probability was 0.3 and we thought that was too high, that can be hard. And so one of the challenges for people using neural networks in financial and regulatory kind of environments is the fact that you really can't explain beyond like, well, we have this model and that's what it did, why it did what it did. So if explainability is important, often people end up having to do other techniques. Though at the same time, there is also the counter argument that like, look, if I have an employee that made a decision, why did they make the decision? Like, well, their brain decided that it seemed like a good idea. Though I guess people are better at coming up with stories. Okay, well, so let's quickly talk about another one. I think maybe a little bit more straightforward. So I have talking to someone who was thinking about this idea, right? So I have a company, have a big data center, not a data center, a customer support center where people call in and ask questions and hopefully get helped and leave happy. And I want to know how well that's going, right? So if I have only a few people, I can just walk in and listen. But if I want to get statistics, you need to actually figure it out. So a couple of possible applications are just sentiment analysis, like we were doing for our reviews. So look, people seem to have good experiences as they called in. Another is trying to understand what the actual topics of conversation were. Here are our biggest problems, for example, that people keep complaining about. So your input is either voice or possibly transcribed text. How would would neural networks be a good solution? I mean, I already put, it's sort of obviously that these days the best thing to do for transcribing speech into text, that is a neural network-based thing. In fact, you can just go use some API from Microsoft or Google or Baidu or someone. But then once you have text, now you have these classification or summarization problems. And then, yeah, there's, we saw a toy example. What might be a problem with just taking that example that we had before from IMDb and trying to apply it here? There's one really simple problem, at least as in the story so far. Right, I don't have labels yet, so someone has to go sit down and label a whole bunch of these examples. You could try to bootstrap that off-the-shelf, model for sentiment analysis of other things, and assume that if people are angry and annoyed about something, they might be, it might do a reasonable job, right? So you can get that to give you some potential labels, and sort of just have to double check them rather than having to label things yourself. Oh yeah, I guess I did have that in there. And then other potential problem is this, again, sequence length, and also, I guess I'll also put it in here. Maybe if the call is on a bunch of different topics, you talk about this and you talk about that, you might be happy about one thing, unhappy about another thing. And if it's too long, then at least the simple approaches that we did won't work very well, right? Because you have to trim out too much. You could probably start with, just taking short snippets and trying to say, look, let me just take a 30-second segment from the end of the call and see if you seem happy then. Okay. I guess questions on these, right? The reason we put them in here is that ultimately this is sort of the point of the workshop, right? Is not to go back and say, okay, great, now I know how to do IMDb. Is to go back and say, okay, I have a different problem. How do I evaluate and think about how I might apply this particular technique? And repeating my point from yesterday morning, really like many other techniques that are not deep learning, and deciding which one makes sense. No questions? All right, let's talk about tuning networks. What's happening here? So if for anyone following along with the slide, the slides and SlideShare, we're going out of order. We're going to do session 6 first, and then we'll come back to autoencoders after lunch. Okay, so at this point, we've talked about sort of all the main types of networks that people use, right? We have our simple feed-forward sort of fully connected networks. We have convolutional networks. We have the various kinds of recurrent networks, including stapling them together using this plot vector idea. You can take, convolutional network and then connect it to a recurrent text network to do captions, things like that. And throughout, we've been saying, okay, Victor, why did you pick all these parameters in these examples? And if you wanted to do better, how would you improve them? So we'll talk a little bit about some tips and recommendations for how to do that, and then go through a bigger example with cars, images, for how you might actually tackle a real problem where you don't know the answer in practice. So some basic things, right? Whatever application you're using, it is always a really good idea to know what good enough means, right? Because in a business context, typically, even if unless you're trying to win some competition, if you know what good enough means, then you can stop when you get there. And you can also see how close you are. Another thing to do is to have some baseline, right? So again, neural network is a big, complex hammer to use. So is there a linear regression model or some heuristic that you have that gives you a sense of how well you're doing? Is your code working? Also a good thing to keep thinking about, right? Oh, my network isn't training very well. Is that because there's a bug and you're feeding it the wrong input, or because it's just not tuned perfectly? Overfitting, underfitting, always one or the other. That's more on the actual tunings, right? And then always keep thinking, can I cheat? Can I solve a simple problem? Can I use a pre-trained model, transfer something that someone's already solved? Right, I guess I have more details on all of these. Well, the additional things to note, right? We talked about this briefly yesterday. Accuracy is not the end-all and be-all of machine learning, right? Sometimes you care about how fast you actually get an answer. When you're doing inference, you might care about model size. We just talked about things like, being able to explain what's going on. So understand your problem fully. Monitoring. We briefly talked about this yesterday. See what's happening. If you're doing a classification task, right, use a confusion matrix to try to understand what kind of mistakes your network's making. We'll see that. Actually, look at your data, right? I'll have some examples later of where things get totally screwed up. And then you're like, oh, my network isn't running very well because I destroyed my data set by accident. Yeah, look at mistakes. Look at the things it's getting right. Look at the things it's really not sure about. Okay, so yeah, most of these things we already looked at in terms of things to look at. The last one I think is also good to keep in mind, right? Look at the actual performance, computational performance of training. Sometimes a little bit of investment in optimizing that can really speed up your process. For code, we've seen some of this already, right? Try to make something that you think your network should trivially be able to do, right? If I'm trying to do visual classification, like just generate some fake images with simple shapes or simple colors. If your network can't learn that, then you're doomed. And so you should fix that before you go try to do something complicated. This is an example that I did later. I was processing car images, and at some point there was a pre-processing function I used that modified things in place. And so then at some point I realized, like, oh, I have an image with a whole bunch of negative numbers for colors. And the funny thing is, the network would probably happily give you a classification for this, right? It's just linear algebra. But it's not going to learn as well for that as for the actual correct numbers. So you got to check things like that. Okay, overfitting, underfitting, I think we've talked about a lot already. Here's a quick question. The one in the middle and the bottom here, what's going on there? The bottom middle. It's not that complicated. Yeah, so you might see weird things in your curve sometimes. We'll see this graph later. Basically, what I did was actually I trained on different data. right? So first I was training on one set of data, and then I added in more training data afterwards. And so basically it was generalizing to new data. And so you can see actually it dropped exactly to the sort of validation level. And then it started to overfit again. So anyway, there's some great learning curves out there. I don't remember if I have a link in here or not.
So you're adding the more data in the middle of training?
In this case, I did, yeah. And that's actually a pretty reasonable thing to do, right? To get a quick sense of like, is this even working? And then once it seems to be working, you can add more data. Or sometimes you decide, you know what, I just need to get more data. So you actually go out and harvest more data from somewhere, label more data, and then you can feed it into your network. So yeah, data, right? Some things that already come up to the degree that your training data is messy and has incorrect labels or is otherwise sort of more complicated than it needs to be, you're going to have a harder learning problem. And so if you can get better data, that can help. We talked briefly yesterday about the need to have small, basically have your numbers be ideally small and are close to 0. That just makes things numerically happier. You can also do things like PCA, principal component analysis, to make the data sort of more orthogonal in different dimensions, which can make it easier to learn from the network. Again, in principle, with enough data and training time, none of that is really necessary, but in practice, it helps a lot. So we talked about this yesterday. If you can get more data, that can often make up for a multitude of sins in all other areas, right? So like a dumb network with a lot of data tends to work better than a really complicated smart model with not very much data. One note here is that there's various options out there for getting labeled data, even if you don't already have it. There's running crowdsourcing stuff yourself to make labels like on Mechanical Turk, and there's also a number of companies that will kind of do that for you. So if you're doing a business thing where you have a budget, often there are people who will help you with that. Okay, so if you can't get enough data, then you have to be more clever. We saw this yesterday for data augmentation, right? So take your existing image, for example, and shift it around. I don't know if people do data augmentation for text. It seems harder, but maybe you can still come up with some ways to, if you were doing sentiment analysis, reorder sentences or paragraphs, or actually for audio data, you can add noise, etc. For visual stuff, it's more common. It's hard. If you had a good enough model to do data augmentation, you wouldn't need to do data augmentation.
For chat monitoring, based on different responses from people, you could potentially do something like this.
Yeah, if you have some kind of structured text application, you might be able to think about how you can generate other examples where you know what the right answer is.
I did a few times, and I get very good accuracy based on the data I generate. Okay, no problem, training, testing. But when you move to live, just completely detailed.
Yeah. So you do want to think about data augmentation. You have to be careful with two things, right? One is it needs to give you realistic examples that will actually be representative of stuff you might see in the world, and two, you need to make sure you don't screw up the labels with your classes, right? So if you flip things around or add too much noise. Sorry, there's a flying platform outside the window. I think they're washing the windows or something. Okay, so yeah, they wanted to learn about model structure. Right? So basic things here, pretty straightforward. Ultimately, you're trying to run this really complicated function from inputs to outputs. If you want to add more capacity, you can make your model deeper. You can make your model wider. You can reduce the amount of penalty you give for weights, for example, so you can have more higher range of parameters. You can have more connections. If you want to have less capacity, you can do the opposite of all those things. And of course, as you do that, training is easier on smaller models, on more constrained models. And it takes less time. So that's always a balance you're trying to play. That's obvious. We talked about this. So specific examples, right, for encoding assumptions where convolutional networks and RNNs. But I briefly mentioned this yesterday. If you know something about your application, and it's not one of these standard things, you might actually be able to encode other assumptions that are not quite as regular as in vanilla CNNs and RNNs. But if you say, look, I think these things should be identical or similar or related, you can try to encode that into your network to force it to be, to generalize better. Yeah, SqueezeNet is a cool example of how to reduce the size of a convolutional network drastically while keeping performance pretty much constant. They, have a way to reduce the number of features in the convolution and then sort of expand it out again in a way that reduces the number of parameters, but turns out to still have enough capacity. You can check out the paper if you want. Activation functions. ReLU tends to be the thing that people use in the middle of a network for most applications these days, because the gradient is 1 throughout kind of the positive side of the function, so it tends to work better for backpropagation and learning quickly. But in some cases, if you want the output to be in some fixed range, you should use something else. So sigmoid we've seen a lot in the output layer for the classification because we want probabilities. There's also essentially a scaled sigmoid hyperbolic tangent, which has output from -1 to 1. So think about what you want. There are many other variants on these, right? There's like leaky ReLUs that aren't exactly 0, for negative inputs, and yeah, lots of variations. You can try them. I don't know if you're really trying to fine tune a network, it's certainly something worthwhile to try. I don't know if that's the first place to start in terms of how much of an effect it has once you have ReLU. Right, cheat. If you're trying to solve a problem, go find someone else that solved something related and see what they did. Right, all papers these days will have at least the model structure, and often they'll actually have a published model. And so start with that. Ensemble methods, right? So this is a common thing in data science in general. If you can make models that make somewhat independent mistakes, you can train lots of those models. You can average them together to get better performance. So this is what sort of the idea behind boosting, random forests, etc. And you can do the same thing with networks, right? Like, I'm not sure which of these structures I should use. Well, just do both, or all 3, or all 10, and then learn, just a linear weight how to combine them. The trade-off is it takes more time, it's slower, it's more complicated to deal with. And so if you're trying to win a Kaggle competition, often people will, staple together 150 different models. If you're trying to run something in production that you have to maintain day to day, maybe 2 or 3, but probably not 150. At least really cost benefit. Optimization, right? I sort of hand waved about this yesterday. I'm going to hand wave a little bit more, but with a little bit more detail. So again, we're learning these crazy million or billion parameter functions that are very nonlinear. And so there's no way you can find the optimal point. Nor do you, again, really necessarily want to, because we want to generalize. So there's all these different heuristics that people use. And yeah, there's a whole science of optimization of these kind of functions to deal with the various challenges of the domain. Some of them are generic. Some of them are specific to networks, like gradient propagation. So there's a few heuristics to keep in mind, right? Initialization of weights, make sure it's random. If you initialize all the weights to be the same, then they're all going to have exactly the same updates, and nothing will ever learn. Tends to be something like -1 to 1 is a good place to start. There's this Xavier-Glorot initialization that tends to work better than just -1 to 1 in that it scales to how big your layers are. And so if you think about it, right, if I'm going to feed stuff into a ReLU, for example, activation function where the input should be sort of somewhere close to 0, maybe a little bit positive, maybe a little bit negative, depending on what's going on. If I feed in lots and lots and lots of numbers that are big, you're probably going to end up far away from 0. So this is a heuristic they came up with for reducing the weight range if there are more and more units. And yeah, Keras, for example, has a bunch of these things built in. So you can just go and say, I want to use Xavier initializer, and it does the scaling for you. Learning rate. If you're using just standard gradient descent, we saw this a little bit yesterday, you want to tune this parameter, right? Explore different values. If it's too small, it's going to take forever to learn. If it's too big, you're going to sort of go off somewhere crazy. Oftentimes, people will reduce it as you go. Like basically, once your learning flattens out, if you drop the learning rate, it can kind of fine-tune a little bit more and get better. So there's heuristics. A number of the other optimizers are basically doing this. They're just behind the scenes trying to automatically tune the learning rate. In some cases, for different using different learning rates for different parameters, depending on how much of an effect that seems to have. There's this great, kind of great Tumblr, lossfunctions.tumblr.com, that has lots of examples of crazy loss functions that people have seen in learning curves, right? So this is not what you want, right? And someone is training, I don't know, 30 different models, and many of them don't seem to work very well. That one down the bottom right is also good. Looks like a, I don't know, heart monitor or something for your neural network. Also, always not well. I mean, place to go look for funny things. So, yeah, a number of different attempts that people have come up with to try to adjust, make learning go faster. In particular, often what they'll do is they look at the per parameter learning rate, right? And they'll say, look, if the parameter isn't changing at all, let me use a higher learning rate for this one and take bigger steps. If it's already jumping a lot every time I make an update, maybe I should reduce it a little bit. And so there's this cool GIF that says, look, if you're at a saddle point, here's how these various different optimizers, how long it takes them to get out of it. And so you can see the red one is just vanilla stochastic gradient descent, and it basically just sits there, going back and forth in the saddle point. And some of the others realize, like, oh, this direction, not much is happening, let me go faster. And yeah, so again, roughly the two tips I would say are, again, see what people have used in similar applications, try some different ones, and use Attograd or Atom as a default.
On the Wikipedia page for stochastic gradient descent, these algorithms are pretty well summarized. So if you're just figuring out like what these algorithms are, I mean, Atom is kind of a variation of Paramus-Prop, so it kind of gives you a little bit of math and.
Yeah. I mean, obviously, you can look up what they're doing to get some intuition. You can also look up what they're doing and read lots of papers about it and get lots more intuition. In the end, I think my understanding of kind of the state of the art is that still no one really knows, right? You have some intuition for kind of what it's doing, but you don't have very good intuition for the optimization problem in hand. And so in the end, you still have to try a few different ones and just see what seems to work.
For this momentum-based,
Yeah.
you feeling like the learning rate is not very important, I would imagine, right?
So a lot of these, are automatically doing learning rate for you. In some cases, they still have a parameter for where to start,
Right.
but I think they typically don't typically you should leave it at default, and then it'll figure it out from there, adjust if necessary. But it is another knob you can tune. One thing that's helpful is, right, you can get a sense pretty quickly of whether it's working or not, often, right? So you just run your thing for an epoch or two with a number of these different optimizers and see which one works better. And like this, you can pretty quickly see, like, oh, okay, this guy moved a lot. This one hasn't even moved anywhere. You could imagine getting stuck somewhere in your optimization and then switching optimizers and trying to make it go somewhere else. You can try multiple initializations. That tends to be really expensive, so people don't do it very often, but you could. It's an art. Right, so batching, I think I've already talked about this briefly. In general, you want to make your batch size as much data as you can fit through your GPU in parallel at once. That's going to sort of speed things up. And the other point that's important that Keras does for you automatically is to make sure you randomize your training data so that you're not learning to fit one particular set of patterns and then forgetting all about that as you learn to fit some other set of patterns, but instead see kind of a mixed set of data throughout. Yeah, so this is a trick that we briefly saw in one of the pictures yesterday for the architectures from a convolutional network that helps a lot in practice. Basically, the idea is that you're trying to learn weights at a particular layer that do a good job of giving useful inputs to the next layer. But as you're doing that, the inputs to the next layer, like the distribution of them, not just the actual values, but overall the kind of numbers you're getting change over time, right? So as layer 1 learns, distribution of numbers you're feeding to layer 2 changes. And that makes it harder for layer 2 to adjust, because it's not just having to learn patterns of the inputs, but it's actually having to sort of adjust the scale of things. If originally you had a bunch of numbers that were around 0, and then they all shifted to be somewhere else. And so people figured out that you can actually do this trick where you normalize between every set of layers, and then give the network the ability to, if it wants to, learn a scale and a shift parameter. So again, this is built in. You can just turn it on. It's good to have some intuition for what it's doing. But the idea is, for every batch of data, right? So I'm taking, say, 32 examples. I'm going to compute the activations for a layer, say layer 2 in my network, and just take the mean and variance and normalize by those, right? Subtract the mean, divide by the variance. So then I always have activations that are 0-centered and univariate. And then, again, there's another parameter this adds to be able to say, you know what, if you don't like that, you can scale it back up and shift it somewhere. And keep track of, how this is overall sort of what the statistics are throughout my whole data set. So then when you test, you're not going to normalize because you don't have a batch, you just have a single element, but you can just adjust by those population statistics to update the activations. And in practice, it works really well for many applications. And in Keras, it's just a layer. So you can say, okay, I'm going to have a convolutional layer, activation, batch normalization, repeat. All right. Questions, comments? A few more slides of sort of tips, and then we'll actually go look at some examples. I think it'll be more interesting. Early stopping. We've sort of implicitly talked about this already. Right? When your validation loss starts to go up, stop training. This is a very cheap way to get regularization. Basically, you can sort of detect when your network is starting to learn stuff that's too specific for training data. And if you're not sitting there watching your network, you can actually automate it using this early stopping thing in Keras, for example, to say, look, if the validation loss hasn't gone down in so many epochs, just stop training. That's a way to save computation. Regularization we talked about briefly. Yeah, often people use L2. So you add up the sum of the squared weights. If you use L1, so just the absolute value, that tends to have, not tends to, it mathematically has the effect of encouraging weights to either be 0 or kind of significant. And so if you're, for some reason, want a sparse network with only some weights non-zero, L1 is, reasons you might want that is, for example, if you're trying to save space, you can represent your weight matrices as a sparse matrix if only a few entries are non-zero. And so sometimes people do that if you're going to deploy on mobile or other reasons or trying to save space. Or in some cases, maybe more for smaller models, if you're trying to actually be able to explain what's going on and say, look, here's only these 7 things impact this parameter. In practice, for large networks, it's still not going to be understandable, but it may help. Dropout, we've seen really the main. Yeah, we've talked about it already. Use it. It works well. Another general point. So lots of parameters to tune, right? One thing that you might be tempted to do is let me just try sort of all combinations in some grid. If you're doing 1 or 2 parameters, that makes a lot of sense. If you're trying to optimize 10 parameters at once, it really does not make sense because the size of your search space is exponential, and random search tends to work a lot better because essentially only some of the parameters typically really matter. Likely to just hit on a point where you're a good value of that parameter. And then once you've done that, you can do sort of local exploration from there to see, okay, this, it was parameter 7, that was really the important one. So yeah, if you're testing, just pick random values in some range for different parameters. And also, we already talked about this with optimizers, like oftentimes you can get a sense of whether it was a good value or not quickly. And if your network isn't learning or isn't learning quickly, you can just stop. Okay, so that was a lot of talking and examples. Let's actually try this out. So we're going to go back to our TensorFlow playground. And we're going to try to see, okay, how does this actually all work in practice? Well, in practice, in the toy example. And first, let's go together for a little bit, and then we can go off. So reset. Right, so we're going to use the spiral data set. It's sort of the most interesting one. Right, it's kind of hard. And let's try to figure out what the effects of all these various different things are, or at least if some of these different things are. So first, let's stick with one hidden layer. How many neurons do you think I'm going to need in this hidden layer to do a good job classifying this? Lots. Okay, so 3. Let's go as far as we can. Let's go to 8 and see what happens, right? So off we go. We're training, nothing is happening. Our test loss is going up, that's bad. This might be a good time to tell you there's a theorem that one layer is actually enough for any continuous function if it's big enough. Unfortunately, I'm not sure that 8 is actually going to be enough for this particular problem. Let's restart and see if a different initialization value will help us. I think we got slightly lower, but our test loss is still bad, right? It's overfitting to a particular pattern over training data. So, doesn't really work. How about, well, what else could we do? So let's add some layers, right? So let's go back to, let's say 4. We're still going to have, let's say, 8 neurons, but now we're going to organize them this way. Is this going to work? It should do better, we think, right? So why is it going to do better? We'll do better. Let's let it train, right? But we hope that it's going to do better because now we can get nonlinear things here in the second layer and then put them together in various interesting ways to, to actually better fit. Whoa. Oh yeah, I guess I was hovering over something. Right, so now before we were getting training loss like 40-something% and test loss 50%, so it was completely useless. Now we're actually getting something like 70+% accuracy, which is interesting. Note that we're still maybe getting better in training. These weights are getting to be quite big. One thing that's sort of silly, if I recall correctly about this simulator, is that if I change this, I think it resets everything. Yeah. Right, so let's add some regularization. Try it again. Note, by the way, that this is a pretty common pattern on training curves, where sometimes it'll be flat for a long time, and it looks like nothing is happening. And it may, in fact, be that nothing is happening, but it may also be that something is happening, and it will eventually finally get its act together and make progress. I'm going to increase the learning rate and hopefully see if that makes it do better. Interesting. So why might this be not working? Any ideas? Look at all these weights. They're tiny. Ooh. 10 to the minus 109. Too much regularization, right? I mean, I didn't really have a good sense of what the scale of this parameter is. That's clearly too much. So let's go down by a factor of 100. Aha. Now we're learning. Right, so now we're actually making progress. So that's good. What else are we seeing? I see it's kind of flailing around a lot, which I can, obviously you can see in the picture here, but you can also see in the up and down wiggling here. That's to me a sign that maybe I should reduce the learning rate a little bit. And sometimes I can make it get a little bit better. In this case, it won't. Weights are still getting kind of big. How can we do better? Right, we're still getting like 70% right. We could probably either add more layers or we can add more neurons, right? So let's add one more layer. Let's say also with 4.
Did you retrain or you?
Yeah, whenever we change the network architecture, it resets.
You can continue training.
In general, you could train, yeah. So there's a number of, well, really the big limitation of the simulator is that every time you change most parameters except for learning rate, it restarts with random data and resets the weights, which is kind of annoying. But it is also the case that if you really change the architecture of the network, it's not clear that it makes sense to keep training from previous weights, right? Because you might have to readjust everything. And procure right out of the layer. So now, like the things that made sense in this intermediate layer before, maybe don't make as much sense. Let me up this so we learn faster. That's also a pretty common thing to see, right? But it gets worse when you increase the learning rate because it takes a jump in the wrong direction, but then it suddenly gets better. So then you have this cliff where, like, okay, now it's actually getting something. It's interesting, right? It's captured some part of the model, but at the same time, these guys, yeah, interesting. Okay, so they're actually not the same. They're overlapping it, so it subtracts them in interesting ways. This one is not, it's not using. These ones it's not really using much. So somehow again, it's in practice, it's hard to tell in real applications, but here, this is telling me, you know what, I probably don't need 3 layers, but I probably do need more neurons. So let's do that. And again, if your takeaway from this is like, it's kind of hard to figure out what to do, even when you can actually visualize your data, that's a good takeaway to have. Oops. It is hard. And there's heuristics, right? So it's wiggling all over the place. Let's slow down a bit. So 90%, getting better, right? We're missing this part of the space. So let's give it more neurons. Overfitting, overfitting, overfitting. But maybe at some point, it'll actually figure it out. Go faster. Boom. Okay, now slow down. Right, so basically 0 training loss, but actually still under 90% on the test set. It's actually also a good thing to keep in mind, right? Like, even though we're getting good performance, if you look at the function that is actually earned, it's pretty clearly not the right function. And that's also, a good thing to remember for your real networks, right? Even if you're getting good performance in your training set, if your test data is kind of outside of the range of your training data, in some, hard to describe way for more complicated things, right? Like here, if you're have a point out here somewhere, some of these points really probably should be blue if the data set actually continues in the same spiral pattern out to infinity. And yet the model we learned is completely wrong everywhere outside of the range. So kind of extrapolation is hard. And so if you train your model on a bunch of images from high quality cameras on sunny days, and then you suddenly give it an image from a crappy camera on a rainy day, all bets are off. What other things matter? What happens if we change the batch size? Right, this is an interesting thing to look at. So let's go to the batch size one. We're going to look at one example at a time. Sometimes it actually works quite well. Sometimes it gives you things like this, where it sort of flails around like crazy, because it doesn't, it's jumping in different directions for each individual data point. So it's much more noisy. But it actually gets, in this case, it worked well, right? It's like, look, no, get this point right, please. If you go to the other direction, it's smoother. But it might actually run slower because you're not, you're making one update every time you look at 30 elements. And also, like, actually, for this data set, I suspect there's a little bit of an effect where, like, different points are trying to push you in different directions, and like, it's harder to wiggle through the space if you're trying to simultaneously, get this point and this point and this point and this point to all work.
Again, from this point, maybe try to go like batch size more.
Again, I think it might reset. Yeah, it resets everything.
Oh,
So
Do you know how many training data is there?
I mean, you can see the points, right? This is,
Yeah.
I don't know exactly. It's like 100 points or something.
200 samples? Or
Something like that, yeah.
yeah, if you don't
And then there's test data. So I guess we can see, right? So if I say 10% training data, then there are something like 20 of each point. So yeah, there's like 200 points maybe. And most of the data is test. So this is actually also a good thing, right? So I have sparse data now, not much training data. And also let's add some noise. Is this going to learn well?
think the RBF function will help.
The what will help?
The Gaussian kernel to project to a high dimension. If that helps, then we need more neurons.
Yeah, you might need more neurons. It's interesting, right? Because it's hard to fit. There's just not much signal. At least if you're a dumb neural network and not a human who can do pattern recognition, like, oh yeah, okay, there's probably a spiral here. But the network just sees the points it sees. And so we're overfitting like crazy, right? It's learned this thing that fits the points that we have, but not generalizing. So now, right, it might actually do better if I reduce the network size a bit. I'm not sure. I'm exploring at this point. But I'm saying, look, I don't want you to learn to fit each point with a separate neuron. That's more general. Which may have some hope. Right, so starting to get at least some vaguely, there's a curve in here. Still not generalizing. Right, this may just be too hard. Overfitting, still overfitting. Right, it's getting worse and worse and worse. It's kind of funny. Okay, well, I mean, you could try to keep going. I'm going to give up and make my life easier, right? So let's get more data. So let's say 30%. Now it might actually work. Go faster. Still overfitting. Now it's starting to actually learn something. All right, but now we don't have enough capacity, perhaps. Right, so let's add another layer. Some more neurons. Go. Aha, it's learning, it's learning. It's funny, it's not really using this one. It's still missing this whole, it's not really using this one. So somehow it seems like it should be able to figure out, hey, I have this free neuron. Maybe I can use it to do something useful here. But so far it hasn't. Let's go up a lot. Check it out of there.
If you're using different feature set, get different.
You mean to add in other features here?
Yeah, X1 sine, X and sine.
Yeah, so this is something well, we can try it. I think it definitely will help. I don't really like it. I mean, I don't know. It's it feels like cheating too much to me because, well, in the sense that for 2D data, it's easy to come up with lots of new features, right? Like, oh, if I have x1, x2, fine, I can multiply them, I can square them, I can do sines, etc. If I have, million point images, it's not nearly as obvious what kind of features to add in. So if you have some intuition for what might help, it definitely is a good idea to try it.
Yeah, because I think there's one very big area we call it feature SDN.
Right.
The whole goal of deep neural networks is
Right. That you can do feature engineering.
Yeah, I mean,
the idea is that it'll figure out like, oh, I think this is a good feature, right, for this network. And the hope is that it figures it out automatically, but obviously sometimes it doesn't. That's what this is. And if you can give it some hints, you have intuition for what's going to work well, by all means, you can feed it in. And yeah, so this worked kind of okay. It's still overfitting quite a bit. Okay, well, I think this gives a sense of what useful things one can do with the simulator, and definitely suggest spending some time playing with it some more. In particular, get a good sense of what these various parameters end up doing, activation functions, etc. Now, yeah, fine. So example. Let's look at some code. Yeah, so looking at this notebook, what I did, with this this example, so this is the next, is try to find a problem that was simple enough to still be a reasonable example, but was a little bit more interesting in that it wasn't an off-the-shelf thing that lots of people have done, and so I didn't know what was going to end up working and how well it was going to end up working. So I just went out and looked for some interesting data sets. I found one, of a size that was non-trivial but still manageable on one computer. So there's this data set from Stanford, Jonathan Krauss et al., with about 16,000 different cars of 196 different models. And I said, you know what, maybe I'll do something interesting with this. In particular, I wanted to think about making a classifier for different kinds of cars. One obvious thing you can do is try to build a classifier for each of the 196 classes, which they wrote a paper out that I did not read on purpose. But I decided to try to see, can I figure out like vans versus sedans versus SUVs, etc. And kind of was a funny thing. A couple of months ago, I found this paper that basically did that using Google Street View images to figure out what kind of cars are on the streets in different places, and then correlated that to various demographic factors like socioeconomic status, actually race, and things like political leanings. Turn out to be very correlated to the kind of cars people drive. And then they can use that to get a much faster estimate of kind of what's happening with all those demographics throughout the US. So things like, if there's lots of pickup trucks, there's more Republicans. Turned out to be, not that surprising, but the fact that you can actually get a good correlation was sort of interesting. So this is actually useful. I'm going to run through the code fairly quickly because I deliberately left in some of my mistakes and sort of like, I tried to do this thing and it didn't seem to be very useful, because the idea is to give a sense of how this actually feels when you're exploring a new data set and not just show you kind of the straight path to a solution. So basically the plan was, okay, get the data, take a look at it, understand what's in there, build a really small model first, just to kind of get all my code working, and see if there's any hope. So what I did is try to make a model to just distinguish two classes, Hummers from like some Acura sedan. And then, once I get some intuition for kind of what was happening with this data set, then try to solve the bigger problem of actually doing classification by different car type, etc. Yeah, okay, so loading Python stuff, get the data set. Where was my, well, maybe I'll skip the whatever data set format. Right, so there's 196 classes. There's a list of them. Right, here's what they look like. We have Hummers, sedans, Aston Martins. I tried to split them up to prepare for my, I want to know what kind of car is it. I ended up doing that later because my first attempt didn't work because it's too messy. the brands are sometimes one word and two words, etc. Data munging, fine. So here's our images. Let's look at some, right? So here's a Hummer. These are all, I don't know what kind of card this is. Here's what they look like, right? Some of them are kind of blurry. Some of them are zoomed in, or like marketing images with a black background. Some are real photos in real life, different angles, etc. So it's going to be a little bit challenging. Try to look at sizes. So most of them are under 1,000 pixels wide, and they're all what was it? Landscape? Yeah, so wider than they're tall. So none of them are huge. Most of them are not tiny. All landscape orientation. Fine. So then the data set actually has bounding boxes for the images. I decided to ignore that to make my life harder. Pretend I didn't have that. Fine. So now you can actually go and plot, one example image from each class, right? So here's our cars. Again, it gives you a sense of the variability. Funny sort of product marketing, sunset shots, stuff on the roads, stuff parked. Here's our van from behind, etc. Okay. Next question was, do we have class balance, right? This came up a little bit earlier with the IMDb thing, like our Scrum class is way overrepresented. Turns out it's pretty reasonable. There's a few that have, I guess there's one that has more than 100 examples, actually the van. And there's a few that have under 60. But for the most part, we're talking about only a factor of 2 between the most common and least common. That's not too unreasonable. So then next is to be able to actually get this ready to process. So I resized them all to 227 by 227. So why is this magic number, right? I know, per Andrei Karpathy's suggestion from yesterday, right? Don't be a hero, use ImageNet models. But that's what I'm going to end up doing at some point. So I was going to do that. And 227 is the size I use for ImageNet. Same size images, that'll make all the models and stuff work well. You could try to actually find the cars and figure out what to do in terms of taking a non-square image into a square image. As a first step, I said, you know what? I'm just going to squish everything to a square image. I don't care if it screws up the aspect ratios. So that's what I did. That was a decision that you could imagine coming back to try to do something better later. Okay, so now we have some data. We have a sense of what it looks like. Let's actually try to use it, right? So like I said, first toy problem is, let's just build a little classifier that I can debug quickly, because I'm only going to look at a couple hundred images, to separate our first two classes, which happens to be Hummer from a sedan. So if we can't do this, then it's going to be harder to do even a general thing. So here's what we're doing, right? Here's some Hummers. Here's some sedans. Obviously not a very hard problem for humans, unlike, say, distinguishing between a couple of different related models. So hopefully we can make some progress. We have, what, less than 90 Hummers and less than 70 Acuras to deal with. So very, very, very few examples. Fine. So load the data, have it explode because there's one image that's grayscale and everything else is color. So fine, convert it back to color. Load the data, and what else does this do? This, I think I have a split later. Yeah. So fine. Get all the files into memory, which I can do because this is still a small data set. Split them into validation and test and training, including shuffling. Remember, we want random order. Fine. So now we have our list of training, test, and validation data. Just massage it to get into the right order. So here's my training examples, right? So now I have 95 Hummers. No, sorry. I have 95 total because out of my 150, I ended up putting like 40% for validation and test, so now I have 95 total examples I'm going to train on, 227 by 227 images, and 3 because it's color. Make 1 hot labels. So, this is an interesting thing, right? I could just use binary and have it output 1 number, but I decided to go with multi-class, with multi equals 2, because I know I'm going to want to do an actual multi-class classifier later. So I just figured I would write that code once. Okay, so let's put a logistic classifier, right? So 1 layer, no hidden layers, right? Just take the pixels, do a bunch of weights, and try to predict from that. This is ridiculous, but we're going to do it anyway. Right, so here's our model. Dense model, output 2, input 227 by 227, and I got rid of color for this toy example. I said, you know what, grayscale should be good enough, and it reduces my number of parameters by a factor of 3. So, fit the model. It takes no time at all, because I only have 95 examples. Wow. Look at that, perfect accuracy, 100%. So, are we surprised by this? No, right? Clearly we're going to overfit if we're fitting 50,000 parameters to 95 images. I'm kind of surprised by this, honestly, right? Somehow it managed, even with a really dumb logistic regression model, logistic classification model, I guess, to get something like 75% accuracy with 50,000 pixels. So it figured out something, but it's not very good. So fine, right? So let's try basic convolutional network. Yeah, that's going to be the next thing. First, I wrote some code to be able to plot the predictions that a particular model makes, so you can actually look and see what mistakes it's making and what it's getting right. So right, here's my training data. Look, it's all perfect. Getting every single one right. I think no mistakes. Here's my validation data and my test data. Normally, again, you wouldn't really want to look at test data this early in the process. But since it's a toy problem anyway, I figured I might as well. Right, so this it thinks is an Acura. This it thinks is a Hummer. This is a Hummer. This is an Acura. Oh, that's actually interesting. No, it's not. I was just looking at this again. I was like, oh, maybe it's like light images with a lot of white that thinks are Hummers. But that doesn't seem to be the case. So even with this model, I can't really explain what it's doing. But I can tell it's making lots of mistakes in generalization. Fine. And ultimately, right, like this is all of my training data. You can just look at it. So that's kind of scary. But fine. So let's use a CNN. We'll try to use dropout to regularize, because otherwise there's really no hope. And I picked 3 layers just because that seemed like a plausible, minimum for this kind of visual data. Okay, right. So convolution, activation, pooling, dropout, convolution, activation, max pooling, dropout. Note that I ended up making dropout optional just to see what effect it has. A small dense layer, just 16 units, and then our classifier. So lots of parameters, 180,000 parameters, 95 examples. Was using TensorBoard just to make sure, get all that stuff set up so you see what's going on. Train the model. And yeah, we're getting something like 85% accuracy or 80% accuracy. It is overfitting somewhat, not too surprising. But yeah, 85% accuracy with 95 training examples on vision data. That's crazy. And no reason it should ever work. But it does. And test, for some reason, is actually a little bit higher. I think that's just an accident of history with the small sample size. But yeah, so I looked at the mistakes. I again didn't really see any clear patterns for what it might be doing wrong. And just for fun, I ran it without dropout. Right, so here's model 2, same model, but I told it to not use dropouts. Train it. Now it's overfitting and getting 80% test accuracy. So it's actually still kind of earned something, but it's overfitting much, much, much faster. So yeah, dropout is pretty cool, is one takeaway. Gradient descent is pretty cool, is another takeaway, that it's earned something useful. And at the same time, if you want good accuracy, 95 examples and training a network from scratch is probably not going to get you there. Sorry, is there a what? So I think it really varies on the domain. A rule of thumb I've seen was something like, if you have 10 examples, then you're probably going to be in good shape, right? So if you have 180,000 parameters, you should have like 2 million examples. Right. So that's again. So that's not true, right? It's not 2 million examples. Right now, I have 95 images, each of which actually has 50,000 pixels. So in that sense, I do have. I'm not feeding it 95 numbers. I'm feeding it 95 arrays of 50,000 numbers. But still, yeah. I mean, more, I guess, is the short answer.
I feel like it's 95. Really.
Yeah. Exactly. Right. If you had 1,000 examples per class for visual stuff, that tends to start to be reasonable. And again, it really depends also on your desired accuracy, right? If you're trying to do even that task I mentioned at the beginning, right? Sort of classifying neighborhoods, if you get 80% accuracy, and then you classify 150 different cards, that might be good enough, right? It's noisy, but who cares? If you're trying to, identify specific vehicle that you're interested in, like that's not going to be good, right? You need really, really high accuracy. Again, of course, right? We can cheat, and we know we can cheat, so that's what we're going to do next. Well, almost next. In terms of the next model, I was like, great. I know I'm going to try to use that thing, but I want to see how well I can do without it. And it's kind of surprising that you can do, 85% without it. So one thing that was interesting, given how few of these things there are, like you could actually go get more data, right? And it'd be pretty easy to double your test size. I didn't do that. I just found like 3 images of each, just in Google, resized them and said, okay, let's test it. And actually got 5 out of the 6 right, which is not conclusive because there's only 6 examples, but it's sort of interesting. Like it really is generalizing to something that I've never seen before. Yeah, and it's kind of consistent with the accuracy we said before. So like reasonable. Since the original data set also came from the internet, I actually quickly checked to make sure none of these were exactly in my training set, because that would be cheating, and they weren't, though something similar might be. Another point, right? Our classifier says any image you feed it is either a Hummer or an Acura, which is not necessarily what you want in real life, right? So here we have a Hummer and an Acura and another Hummer. Right? If you have vision tasks, or really any other task, classification tasks, where there's sort of a none of the above, you need to make sure to actually train with that. And it can be quite challenging because it's hard to describe what all things in the world that are not Hummers and Acuras look like. Right? So how do you get a representative set? But you can try. Okay, so right now let's actually go to the class separation. So classifying the sedan, SUV, pickup, etc. I actually did the manual, semi-manual parsing of the various of those car type strings into the various things. Right, like here's going to be my car types: SUV, sedan, convertible, coupe, wagon, minivan, and van. So 7 classes. Map everything appropriately, parse stuff, blah, 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 blah. Fine. So we get, now we have an uneven class distribution. There's a lot of sedans and not so many vans and minivans, for example, which may make our life harder. But we're going to cheat. That's going to make our life easier. Fine. So whatever, just data munching details. I'm skipping, load the data, convert now to our new sort of macro class labels. Now we're going to use basically exactly the same model that I tried before. Still 3 layers, still the same convolutions. Only changes now in my output layer. I'm putting out 7 classes instead of 2. And so if I'm going to train, right? So now I'm training on all my data and with 7 classes. Or is it 8 classes? I thought it was 8 for some reason. Maybe I was wrong. Sorry. Not that it really matters, but 1, 2, 3, 4, 5, 6. Yeah, it is 8. Okay. I guess I missed one. Up there. So what's happening here? Underfitting, right? Like it's generalizing pretty well. And in some ways, it's kind of cool that even, again, without cheating yet, I'm getting 35% with 8 classes. Of course, they're unbalanced classes, but still doing something kind of reasonable. And it's so far, it seems like you can keep going and it'll just keep learning. So I did that for a while. And it was still learning, but definitely starting to overfit. And it's more clear on the loss. Like it's pretty flat for the validation loss. So I said, you know what? Well, again, I know I'm going to want to use ImageNet anyway. But in terms of building up tools, let's look at confusion matrices and see what kind of mistakes it's making. So I made a function to plot confusion matrices. Right, so here's the true label, what it should be called, and here's what it actually gave it. And so sedans, for example, are mostly right. And it's getting a lot of correct stuff there. SUVs are actually also like half of them are right, and the other half it thinks they're sedans. Pickups are pretty much all wrong. They're all either SUVs or sedans. Coupes, not really surprisingly, it's confusing for sedans. Convertibles, confusing for sedans. It never used the label minivan, never used van, never used wagon, right? So like everything is a sedan or an SUV, or maybe a coupe. So that tells me something. Again, it's not that surprising given the class imbalance that it's overweighing the high frequency classes. And if I didn't have ImageNet, you could go about trying to fix that by oversampling your lower frequency classes. So looking at those more, you could do data augmentation to sort of make more images of vans and wagons, etc. And moving on to the next notebook. If you're following along in the notebooks, let's cheat. So I'm skipping all the header code that's basically just loading all the things again and getting it all set up again. Somewhere over here, we're going to, right, so this is the same confusion matrices with a little bit more discussion, but ultimately, who cares? Looked at some of the mistakes, didn't find anything. I was wondering, for example, for coupes, whether, right, coupes, 2-door versus 4-door, pretty easy to tell if you're looking from the side for as a human. Pretty hard to tell if you're not familiar with the model, if you're looking from the front or back of a car. So I thought, oh, maybe that's what it's learned, that it's getting them right if it's from the front or from the side rather, and getting it wrong from the side. It wasn't clear that's what it was doing, so I didn't actually count. So let's go with ImageNet models. So in this case, I decided to use SqueezeNet just for fun, which is an ImageNet pre-trained model that's small. It's like a few megabytes instead of the others, and fewer parameters instead of the like VGG or other models that are hundreds of megabytes. So fine, I loaded it. Right, so just to train it on the original ImageNet classes, if you give it this image, it says sports car, drivability 54%, car wheel, drivability 42%, convertible, beach wagon. It thinks it's a 1% chance this is a beach wagon. But so clearly it's, it knows about cars already, which is good. Here is my screwed up image that I mentioned earlier, where I accidentally destroyed my data a little bit during pre-processing, so I had to fix that. So SqueezeNet is this really, really deep network, right, with a whole bunch of convolution activation pooling. Actually, I guess there's not as much pooling, but like layers and layers and layers and layers and layers and layers and layers. And then suddenly, well, not suddenly, finally at the end, we go to our 1,000 class classification layer. So just like yesterday, what we're going to do is we're going to rip off this 1,000 class classification layer and build a new classifier just on top of these 13 by 13 by 512 like final feature maps for the images. So really, it's more or less the same code that we saw yesterday to pre-compute bottleneck features and right. So right, scroll. We ripped off those final things. So now we're going to stop here for the last internal layer, and yeah, this is also where we're going to see that adding more data. So I figured, let me start with a small set. So rather than my 16,000 images, I'm going to just look at 2,000 to start. So I did that. Compute the features. They're already pretty big. Make the new model. So I'm just adding a convolution. And this thing, I guess, is new global average pooling. So this was the yesterday when we were talking about convolutions, we said there were two ways you can take that into a classifier. So this is the way that you sort of make the one feature map for each of your classes, and then just average across space. Or in this case, at average, you could also max across space, and use that as a classifier rather than having a dense layer. And that's actually what SqueezeNet did before as well.
And if you really talk about everything, why do you want another?
It's a 1-by-1 convolution.
Oh.
So essentially, yeah, it's really just changing the number of layers. So before I had 13 by 13 by 512, right? So at each of the sort of 13 by macro regions in the image, I have 512 different features that we know are useful. And now I'm saying, okay, make it into a 13 by 13 by 8 feature map. So figure out a way to map those 512 things into 8 different things at each pixel independently, and then just average across the 13 by 13 space and use that as a prediction. So it's just another way to do to make a classifier. The benefit is you can deal with different size images because all your convolutions sort of, you can slide across any size image, and in the end, you just average across the space dimension. And so that's why people use this approach. Stick it together with those same inputs. Only has 4,000 parameters to train. That's good. We like that. And there we go. Out of the box, 88% or so, 90% validation accuracy.
There's a question online. For getting a good idea of the number of neurons per layer versus number of layers, can we not use hyperparameter tuning like quick search or random search or something like that?
Yeah, so that's a great question. The question is, well, I guess you guys can see it in Slack if you're online. Can't we use YouTube chat? Can't we use parameter tuning methods grid search or random search or something to decide how many layers to use and how big the layer should be. Yeah, you absolutely can. Just there's a lot of space to explore, right? You can go from 2 layers to 20 layers, or modern networks have hundreds of layers sometimes, and each one can have a different width. So there's almost infinite parameter space to explore. It helps to have some idea of what's likely to work, and you can get that from just by looking at what has worked for other people and then exploring from there. But absolutely.
We're going to talk about some of those options in the scaling and the Spark section in that one also.
Yeah, so Shreyas is saying that we'll talk a little bit more about how to do that from a more sort of operational perspective with Spark and things like that this afternoon. Okay, so yeah, ImageNet. It's a great way to cheat. 8 classes, 90% accuracy, with really not much work on my part so far, right? You can look at the confusion matrix again. Now it's much more diagonal, and we like that. It's still confusing convertibles and coupes for sedans a fair amount of the time. And I guess wagons for sedans as well. So that may be due to the fact that it's just a hard problem. And it also may be due to the fact that the classes are unbalanced. So you could certainly continue further to mess with it. If I recall correctly, I didn't. Well, I guess one thing I did after this is throw in the rest of the data, right? So rather than just my 2,000, I put in the rest of the data, and that's where it bumped up the accuracy by another couple of %. So more data is helpful, especially when you're overfitting. And then I stopped. Yeah, so validation confusion matrix. Now it's at least using all the labels. Still making mistakes. Lots more stuff you could do if you wanted to really continue tuning this, right? You can do data augmentation. You can go back to the decisions I made earlier on, for example, resizing and change them. You could add one more layer on top of the SqueezeNet thing, so not just go directly to a classifier. You could try other pre-trained models. Yeah, so hopefully that was a good sense of, okay, still a brief walkthrough, but for a bigger, more complicated problem, here are some of the ways you would go through and tackle it. So we're going to take a break for an hour or so, 50 minutes, something like that, and then come back, talk about autoencoders and Spark, and then more stuff after that. So I'm going to stop the broadcast if I can find the window.